This is the first lecture of the course, and as you see in the course syllabus, we are starting with chapter 2, and that chapter deals with stereoisomers or stereoisomerism. In this presentation, we will cover the following: definition of isomerism and isomers. Next, we'll look at representations of molecules in three-dimensional space. And the last part of the lecture will deal with stereoisomers, and more specifically enantiomers and diastereomers. Notice I put here that a model set may be needed to fully grasp the concepts covered here. You'll see that in this lecture, and of course in organic chemistry, we're dealing with molecules in 3 dimensions. So we'll have to visualize these molecules in 3 dimensions, but unfortunately, the way we communicate with each other is in 2 dimensions. That's on a piece of paper or on a computer screen, which makes it challenging to fully grasp the 3-dimensional arrangement of the atoms in a molecule. So let's start by looking at some basic material here. And this is 2-chlorobutane. And this is the ball and stick representation. So in other words, if you had your model sets and you built 2-chlorobutane, this is a snapshot of what you would get. But notice again, it's a snapshot. It tries to capture the 3-dimensional arrangement. So in other words, this chlorine here is in front and that hydrogen is in the back, as shown here. Another representation that we often use in organic chemistry is the expanded structure. So here is a carbon, here's another carbon, 4 carbons, and the chlorine here is on carbon number 2. So of course that's why it's called 2-chlorobutane. As you can see here, this structure here does not communicate very well the 3-dimensional arrangement of the atoms in space. So let us look at some representations that have been developed over the years. The first is the line angle. So here we have the line and an angle. Wherever there's an intersection and an angle, that's a carbon. Wherever there's a start, that's a carbon. The hydrogens, of course, as you know, are not written in, just the heteroatoms such as chlorine. Another representation that's frequently used in organic chemistry is the dashed wedge representation, where of course, as you will recall from your sophomore organic, the dash and the wedge represent the different orientation of the groups in the plane, or behind the plane, or in front of the plane. Here is a wedge, and that means that it's in front. Here is a dash, and that means that it's behind. So again, this type representation gives us a good description of the atoms that are in front of the paper and the atoms that are behind the paper in a different plane. Of course, the lines here represent the atoms that are in the plane. So here are the atoms here that are in the plane. This is in front, that's behind, in front, and that's behind. So that's the dashed wedge. Another representation that's frequently used in organic chemistry to represent the three-dimensional arrangement of atoms or groups of atoms is shown here as the Newman projection. So here we're actually looking down this carbon, and there's another carbon behind that carbon. This carbon in front has a chlorine, a methyl group, and a hydrogen. Could be this carbon here, looking down this direction now. And behind is the other carbon, which has on it a hydrogen, and a methyl, as shown here. So this is the Newman projection. Another projection that's often used in organic chemistry is, of course, the Fischer representation. It's just a cross where this carbon here has 4 groups bonded to it. The groups on the horizontal are in front, and the groups on the vertical are in the back. So this is in the back, and this is in the front. So if you have your model set, you may want to just orient your molecule to show 2 groups right across from each other, that's in front, and 2 groups vertical would be in the back. You'll see the importance of this in a second when we really analyzing stereoisomers, which really are the descriptions of isomers in 3 dimensions. But before we do that, let us look at isomers. So as you will recall from even your Gen Chem, isomers are molecules that have the same molecular formula, but the arrangements of the atoms are different. So this is taken directly from the book. So we can do this analysis. If we have 2 molecules that have the same molecular formula, if we ask the question, are these atoms bonded in the same order for the 2 compounds? So we're analyzing 2 compounds here with the same formula. If no, if the atom to atom bonding are different, then we have what we call constitutional isomers. Some books you'll see it written as structural isomers. We can go further. If we ask, are these functional, are they the same functional groups on the molecules, on the 2 molecules? If no, they are functional isomers, and if yes, they are positional isomers, where the functional groups are positioned differently in the molecule. I have an example on the next slide. Here is where we will place most of our emphasis, though, in this course or in this chapter. If the answer is yes, so if the connectivity between the atoms, same molecular formula, same connectivity, atom A to atom B to atom C, they are the same for 2 atoms, then what we have here is the possibility of stereoisomers. Stereo here, of course, as you know, means the orientation in 3-dimensional space. If you ask yourself a further question, are these structures mirror images of each other? Keyword here is mirror images. If the answer is yes, we have a special term that's called enantiomers that we'll define and give examples of in a second. If they're not mirror images and they are stereoisomers, a possibility here exists that they are called diastereomers, and we'll give an example of diastereomers in a second. But let's look at another representation just to illustrate this some more. So we have isomers. If they connectivities are different. We have constitutional isomers, as we said last slide, or structural isomers. But over here, if the connectivities are the same, so the bond to bond to bond to bond connections are the same, then we have stereoisomers. So here we have the possibility of enantiomers or diastereomers. We have another type isomer here that's described as cis and trans. As you may recall, this has to do with a rigid framework where there's no rotation. So let us look at some examples here. So here's an example of C4H10O. So here's a molecular formula. Notice the molecular formula does not give any idea of the structure of the molecule. In organic chemistry, we typically need to know the structure of the molecule so we can identify functional groups and we can identify possible reactions. So here is C4H10. One possible isomer is here, still C4H10, another one is here, and a third and a fourth. These are all alcohols because of that group, functional group that are present, and because of that functional group that are present, it's called positional isomers because of the position of the functional group. Here is another isomer, and this one, of course, here they're structural isomers, as we said here, and notice that the atom to atom connectivity of this is different from this one, etc. This functional group here, as you will recall, is called an ether. So these are all ethers here, but they're structurally different. So they are called positional isomers because of the position of the functional group here is different. But the relationship between any one of the alcohols and the ether are now called functional group isomers because of the functional groups that are different. So that's what we'll say about structural isomers. So let's go into stereoisomers. So for stereoisomers, remember that the atom to atom connections for any two molecules will be the same. So let's look at these two molecules here. This is 1,2-dichloroethane, 1,2-dichloroethane. Same connectivity. However, based on the rotation about this bond and the bond carbon in the back, it's possible to have the anti and another contour called the gauge. So these are called rotational isomers or conformational isomers that differ only due to rotation about a single bond. We'll see examples of that before too long. So these are conformational isomers. Make sure that you remember these terms and of course the definitions, because we will be using these terms whenever we communicate. Another type isomer is called the geometric isomer. Notice again it's an isomer and a stereoisomer because of the atom to atom connections are the same. Chlorine, carbon, carbon, chlorine. Chlorine, carbon, carbon, chlorine. Same connectivity. However, this is called a geometric isomer because we have a rigid system here, a double bond, which has restricted rotation, or in other words, not even restricted, no rotation. So that's why we have the trans isomer and the cis isomer. This trans, of course, is across from the plane, chlorines, and the cis mean that these two groups are on the same side of the plane. So these are two types of stereoisomers. Let's see if there are other types of stereoisomers. So let's look at this picture here of two molecules. So what we have here are two molecules. We have a carbon, and it's the ball and stick model, of course, as you see here, which has a white, yellow, green, and red, and the same white, yellow, green, and red. So these two molecules have the same atoms, they should have the same formula. The question now is, are the atom to atom connections the same in space, in three-dimensional space? So another way of asking that same question is, are these two molecules stereoisomers, or are they the same? That's a tricky question, because you'd have to do quite a bit of analyses here to make that determination. So if you ask a question of this type, typically you have to resort to a principle to make a conclusion, and here's one you can do. One criterion that can be used here is if they are the same or stereoisomers. So we can use this criterion to determine if two molecules which have the same groups bonded to a carbon, or four different groups bonded to a carbon, if they are the same or not. If they are superimposable on each other. So in other words, if they are superimposable on each other, they are the same molecule. If they are not superimposable on each other, then they are stereoisomers. So the two molecules that we had on the previous slide, you can see here that they're totally superimposable on each other, where the red overlaps, the green overlaps, the white overlaps, and the yellow overlaps. Therefore, conclusion, these two molecules are the same. Let's take it a step further. Of course, as you know, in organic chemistry, we will not be using models to communicate. We'll not be using ball and stick models to communicate, but we'll be using one of the representations that we just described, the dashed wedge, or the Newman, or the Fisher, to communicate and draw molecules. So the question now becomes, looking at these two molecules here, are they the same or are they different? So what that requires is, if you can superimpose them on each other, they are the same. If they are not superimposable on each other, then they are different. So as you can see, this stereochemistry or stereoisomerism in organic chemistry requires a lot of perceptive thinking and analysis. Okay, so what you have to do is to really analyze this, and I think this one has the answer here. So you can see here that they are superimposable on each other. So give that a try, and therefore they are not stereoisomers, but they are the same. They are superimposable, so therefore they are the same. Notice again, they are drawn with groups here: bromine, hydrogen, ethyl, methyl, same bromine, hydrogen, methyl, ethyl, same groups that are bonded to the carbons here, but we'll have to look at the orientation of the atoms or the groups in space. Okay, let's take it a step further. So here are two molecules. Here we have, with the same groups bonded to it, carbon, white, green, red, and yellow, and another molecule with the carbon, a red, yellow, white, and green. So it has the same molecular formula, same groups bonded to the central carbon, but there are four different groups bonded to the central carbon of both molecules. The question now is, are they the same or are they stereoisomers? So the test here, of course, is to determine if they are in fact superimposable on each other. So what you can do is to imagine taking them up in your mind and twisting them around or using the real molecule, and you will see that they are not superimposable. The whites and the white overlap, the red and the red overlap, but the green and the yellow, they do not overlap. So therefore these molecules are not superimposable. So therefore they are not the same, and they are stereoisomers of each other. They are stereoisomers of each other. Let's take it a step further. The same two molecules that are not the same but are stereoisomers of each other because they're non-superimposable, it turns out that they are mirror images of each other. If you can imagine this to be a mirror right here, here's molecule 1, here's molecule 2, the white reflects, the yellow reflects on each other, the red reflects, and the green in the back reflects in the back. So therefore this is the mirror image of this molecule here. If two stereoisomers are mirror images of each other, they have a special name and they are called enantiomers. They're called enantiomers. So your job now becomes, can you look at the representation or one of the representations that are typically used? Here is the dashed wedge for two molecules that are isomers of each other, and tell if they are enantiomers or the same. So in this case you'll have to determine if they are superimposable or non-superimposable, and if they are mirror images, if they're non-superimposable of each other, then they would be enantiomers. It turns out that here's another representation, the Fisher projection. So this is just using the Fisher projection here, another representation to reflect the three-dimensional arrangements of atoms around a central around a carbon. Here's a central carbon. This is in front, that's in front, that's in the back, and that's in the back. Same here, back, back, and front, because it's the Fisher projection. Looking at this, the question is, are they the same or are they enantiomers? One way you can look at this is quickly determine that if a mirror was right here, this hydrogen reflect, the amine group reflect, and the carboxylic acid reflects, and this is in the back. So therefore these are mirror images of each other. They're non-superimposable on each other. So therefore they are in fact enantiomers. So these are enantiomers. So again, the bottom line is you should be able to determine enantiomers or molecules being the same based on the different representation, such as the dashed wedge, the Fisher, or even the Newman projection. Let us look here at another way of writing this. So here we have two representations. This is the Fisher and this is the dashed wedge. It's the same, they are molecules that have the same groups bonded to this carbon, an ethyl, hydrogen, carboxylic acid, and amine, and a methyl right here, pardon me, and a methyl, amine, carboxylic acid, and hydrogen. So they have the same groups bonded to this carbon, but now it's represented in the Fisher and the dashed wedge. Two representations trying to capture the three-dimensional arrangement of this. So the question is, what is the relationship? Are they the same or are they enantiomers? So you should be able to carry out the manipulation here to make that determination, and again you may use your model sets here, but close inspection shows that they are superimposable on each other, hence they are the same. So be able to do that. We'll see in a second that we have a much easier way to determine if two molecules that have the same groups bonded to, 4 different groups bonded to the carbon if they are enantiomers or the same. But we have mentioned enantiomers. Let's see if we can determine the importance of this type chemistry here. Enantiomerism, or different enantiomers, play a very important role in biology. For example, for enantiomeric molecules to fit, must fit perfectly in the active sites to have biological activity. As you can see here, here we have a molecule here that has 4 different groups bonded to it, A, B, C, and D. And here we have another molecule which has the same 4 groups bonded to this carbon. However, the active site fits B, C, and D in this format. So only this stereoisomer will fit this binding site. This stereoisomer, however, will not fit, as you can see here. And this, of course, is the enantiomer of this, because if you put a mirror here, this is the mirror image of that. So that's very, very important for biological activity. To be more specific, here we have two molecules, or really 4 different molecules. This is the enantiomers. These are enantiomers, carbone and carbone. Here's the enantiomer of this one. We'll see why we call it S and R in a second. But the bottom line is that one of these, it smells like mint, and the other one smells like spice. In other words, the sensory aspect of our smelling can detect one enantiomer over the other. Here's another one, thalidomide. Again, two enantiomers, and as you can see here, it differs around this carbon. And back in the 60s, this was used as a cure for morning sickness for pregnant women, but only one did the job. The other one caused gross birth deformities. So that's another indication that the body can actually detect one enantiomer where it does good, and the other enantiomer is really bad. So that's very important in organic chemistry. So let's look at another system here of determining different enantiomers. So we'll look at the naming. Of course, as you know, if they are enantiomers, they are really different molecules, stereoisomers. So they must have different names. And Kahn, Ingold, and Prelog came up with the RS assignment. And this is a review again, because you did this in undergraduate organic. So what's done here is you have a carbon here which is described as a chiral carbon. Chiral. By that I mean a carbon that has 4 different groups bonded to this carbon. We have here 4 different groups bonded to this carbon, so therefore it's described as a chiral carbon. Using the R and S assignment, it states that you assign priorities based on atomic numbers to the groups bonded directly to the chiral carbon. Chlorine has the highest atomic number of these. Fluorine has the next, so it gets number 2 priority. Carbon has the 3rd priority, and hydrogen has the lowest priority. So you look at the periodic table, you'll see that chlorine, the atomic number here is 17. It assigns number 1 priority. Fluorine here has atomic number 9, assigns number 2 priority. Carbon here has atomic number number 6, assigns number 3 priority. And hydrogen has atomic number 1, the lowest priority, number 4. In using the R and S assignment, It says to orient the group of lowest priority in the back. Since this is the Fisher projection, this is automatically in the back. What you do is trace from 1, 2, and 3. So we go 1, 2, 3, and back to 1, and you can see that goes in a clockwise direction. So therefore that's assigned an R configuration, an R configuration if it's clockwise, just like the clock. As you can expect, going in the opposite direction, so this would be the enantiomer of the previous slides. So going in the opposite direction, we go 1, 2, 3. Here we go counterclockwise, opposite to the movement of the clock, and this gets an S assignment. So that's an S enantiomer. So again, by assigning S and R, we can determine if these molecules are different or the same. If you have two molecules that have the same groups bonded to it and both have the S assignment, they are the same. If both have the R assignment, they are the same if they have the same groups bonded to it. But if they are R and S with the same groups bonded to it, they are enantiomers. Okay, let's look at this one here. I think here what we wanted to show you that, yeah, if this group is in the back, lowest priority, you go with that. But if it's not in the back, here's the Fisher, the horizontal, this is in front. As you can see, it's not in the back, so it's opposite to that assignment. So in other words, just refresh this aspect in your organic chemistry undergraduate textbook. But you should be able to assign R and S to any molecule, any stereoisomer that is chiral. Chiral has 4 different groups bonded to that central carbon. Let's just conclude by looking at an example here. So we have here bromo. So we have 1, 2. So that's an ethane. And then we have 1 bromo, 2, 1 chloro. So it's 1 bromo, 1 chloro, ethane. 4 different groups bonded to this carbon. So therefore that is a chiral carbon. Its mirror image is shown here, so therefore these are enantiomers. If you do the absolute assignment, this is an RS and this would be an R. So this is one way of determining that they are actually enantiomers. So now you can see you have quite a few ways to determine enantiomers. One is mirror image. They're mirror images of each other, and they have 4 different groups bonded to it. They are enantiomers. Number 2, if they are superimposable, if they're non-superimposable and or mirror images, then they are enantiomers. If the absolute assignments are different, providing they have the same groups, they are enantiomers. Here's another representation. This is, of course, a dashed wedge. This is the Fisher, and you can see that they're mirror images, but doing the absolute assignment, you can see this is S and that's R, so therefore these are enantiomers of each other. Okay, let us look at another possibility here, and this is the possibility of 2 chiral centers. Notice again, a chiral carbon is a carbon that has 4 different groups bonded to it. As you can imagine, organic molecules, they get very complex and very large. So it's possible to have a molecule that has more than 1 chiral center. The question now is, are there enantiomers still, or how do we analyze this? So here we have 3 representations of the molecule, or ball and stick. Here's a carbon with 4 different groups, yellow, red, white, and of course this is another group. Here's a carbon which has yellow, green, and white, or green is on the back, white is in the back. So we have 1, 2, 3, and all of this is another group. So we have 2 chiral carbons here. We have 2 chiral carbons here. One is in front, and that's in the back. So this would represent your dashed wedge. That's the in the plane, in front, and back. So that would be a dash, and in the back, which you can see, would be a dash. Here's your Newman. So this is in front, and we have these 3 atoms bonded to that front carbon. In the back carbon, we have here the red, white, and yellow. And here we have another representation, and this is known as the fissure, where the horizontal in front, and these 2 atoms, yellow, would be in the back. But the bottom line is, this carbon is chiral, that carbon is chiral, the one in the back is chiral, because each has 4 different groups bonded to that carbon. Now the challenge comes in representing these using conventional representation. For example, the fissure. Here's a fissure. And of course, since this carbon is chiral, we can determine if it's R or S. Since this carbon is chiral, we can determine if it's R or S using the priority rules. Here's the dash wedge. This carbon is chiral because it has 1, 2, 3, and 4 different groups bonded to this carbon. This carbon is chiral because it has 1, 2, 3, and 4 different groups bonded to this carbon. So we can determine if it's R or S. Based on the determination, it's S and S. Another representation here is a Newman. Looking straight down, this carbon is in front with 3 groups bonded to it, and it's also bonded to a carbon in the back which has these groups bonded to it. So again, you should be very comfortable in using any one of these 3 representations to communicate the 3-dimensional arrangements of groups around an atom using these representations. So the name of this molecule here would be 2s2s because of the absolute configuration here. Let's just conclude by looking at another type of stereoisomers. So let's look at this. So here we have the Fischer projection of this molecule. It has 2 chiral carbons here. Its mirror image is right here, so therefore these are enantiomers because they are mirror images of each other, and they are non-superimposable. Let's look at these molecules here. These 2. Here's a mirror. So this is the mirror image of this molecule. And they are enantiomers because they are mirror images and they're non-superimposable. Notice again, this is S and S. The mirror image or the enantiomer would be R and R because it would be opposite. Notice again the relationship here, enantiomers S and R. In the enantiomer, it would be R opposite to S and S opposite to R. So therefore these are enantiomers. Now comes the question, what is the relationship between these 2? They are not mirror images. They are not enantiomers. As you can see here, these don't reflect on each other. So they are not the same. They are not enantiomers, and they're not mirror images of each other, but they are stereoisomers because of the same atom-to-atom connectivity that we described earlier. the term that's used here is these are diastereomers. So diastereomers here are non-superimposable mirror images that are not enantiomers, but they are still stereoisomers, and they are called diastereomers. I think this is the last slide here. No, okay, we have here. So this is just a little more illustration of the diastereomers. So here we have R and R and R and S. So they are not enantiomers, because if they were enantiomers, they would be opposite. They're not mirror images, as we can see here, because if you put a mirror right down here, they just don't reflect on each other. So they're not enantiomers. So the conclusion is that they are diastereomers. Remember, diastereomers are non-mirror images that are not enantiomers of two molecules, two isomers. I think the next slide here is the last one, just gives us another representation of the two molecules. So here's a dashed wedge, and here is the Newman. So you should be able to look at these two molecules again and determine if they are diastereomers, or are they enantiomers, or are they the same. So we'll do that in the next lecture. But again, we're just covering some of the basics, or reviewing some of the basics in this first lecture here. I think this is the last slide. No, this is not the last slide. This is the last one that gives us the actual answer. So for the two molecules before, we have the S and the S, and then this is also S and S. So with that said, that they are not, that they are the same. So as we can see here, they are the same. On the other hand, if the assignments were exactly opposite, they would be enantiomers, and if they are different, they would be diastereomers. So let's just conclude on that, because these two assignments are the same, S, 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 and the groups bonded to each carbon are the same. They are the same molecule, these two. If, however, this were R, and this were R, and this is still S and S, then that would be enantiomers. But if this were R, and this is S, and this is S, and that's R, then they would be diastereomers. So we'll conclude here, because we'll pick it up here and review some more, and then we go into more complex discussions of stereoisomers. So that's the end of this first lecture. So continue reading in your text, and I will prepare another lecture shortly before the end of the week on stereoisomers, but continue reading.